Hey, Physics 2018, this is Mr. Lewis. So, like I told you, I'm going over some of these ones out of the study guide. I'm going to start off here with number 4 to 7, this conservation of energy problem, because it seems like a lot of people in class were having some trouble with it. So, here's what's going on. Let's start with number 4, because you always want to start at the conceptual notion of what's going on here. So, explaining the energy transfer. So, again, we're talking about mechanical energy, because it tells you right here, assume mechanical energy is conserved. So, mechanical energy, remember, is your GE, your EE, and your KE. Okay, gravitational, elastic, and kinetic energies. So let's think about this whole thing. We're starting at the top of a bridge. We're going to jump off with a bungee cord at 100 meters from the edge of the ground, so halfway down. And that's just a coincidence. That doesn't mean anything. At halfway down, the cord is going to start to stretch, and then eventually it'll stop him once the cord has stretched out to 40 meters. So at 200 meters, we're on the bridge. At 100 meters, then that'll be the point where it's just before the cord stretches. Then from 100 through 60 meters, now, why did I say 60? Because it says that the cord stretches 40 meters. If it stretches by 40, then you have gone down 40 meters further than when you were at 100. So 100 minus 40 equals 60. So between those two spots, from 100 to 60, the cord is stretching, slowing him down. Okay, so that's happening. And then at exactly 60, so at 60 meters, he stops. And then about to spring back up. Now, I have not explained anything about energy just yet. But I have, what we do have here is a nice kind of outline of what's going on. But let's add a quick note here for the interval between 200 and 100, because in there, well, we have 200 to 100 meters. Take on it. We have falling normally, because nothing's happening there. The bungee cord's not doing anything until it actually gets all the way to where it's about to stretch. So we really have 5 bits of what we're talking about here. So now let's talk about energy. I'm going to make me a little line barrier. So what's going to be happening here? So let's consider all of our energies. At this point up here, when you're just standing on the bridge, you have all GE. You only have gravitational energy. You're just standing there, so there's no kinetic. The cord is not doing anything yet, so there's no elastic. And you're definitely up in the air, so you have gravitational. And as a matter of fact, you're never on the ground. You're always above zero, so you're gravitational in every single one of these. But one thing that you can say for sure, in all of these after the first 200, you're lower. You're lower to the ground. So in every single one of them, we can also say that GE is decreasing. That's not how you spell decreasing. There we go. So, sorry about that, excuse me. So we know that the gravitational energy is decreasing every time that you're going lower. So I'm going to go ahead and put that in every single space. G is decreasing. GE is decreasing. GE is decreasing. And then at this point, GE is the lowest. It doesn't get any lower than that, because you don't go any lower than that. Okay. After this point, you could consider, if you wanted to, that he, goes back up again. But the problem stops at the part where the guy stops moving. So after this is not important. But you know pretty much that if energy is conserved, he's just going to do the exact same thing in the opposite direction. The spring is going to pull him back up, the bungee cord is going to pull him back up, and then he'll, speed up going upwards. And then once it runs out of cord elasticity, he'll be in free fall basically. He'll just be slowing down against gravity. But again, don't worry about that part. That's okay. Now, gravitational energy, we know what's going on here. So this is all GE, and then it's decreasing, 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 and then it's a minimum gravitational energy. Now, as you start falling, well, now you're moving. So you start getting kinetic energy, right? So you're falling, and it's increasing that whole time, right? So at the expense of that gravitational energy, you're losing this in order to gain this. Gravitational goes down, kinetic goes up. The total amount, though, the total amount if you add those two together at anywhere in this whole thing, because energy is conserved, GE plus KE anywhere needs to equal the original, what it was as just gravitational energy. Because that's the whole deal with mechanical energy. That total mechanical energy can't change, ever. At the beginning it was just GE, so then that is the total mechanical energy. It has to be this number for the entire time, and that's going to be important there for number 5. So keep that in mind here for just a second. Right? So after this, so we're at 100 meters just before the torque starts to stretch. GE is still going down. This is where KE is biggest, because he's sped up all the way to this point. Because, you know, you accelerate when you fall. So all the way from 200 to 100, he's getting faster and faster and faster. So as GE goes down, KE goes up. Now, that's what the chord's going to do, is it tells you in the problem, is the chord stretch eventually stopping him. So once the chord starts going, you're going to have an opposite force that's going to start slowing him down. So during this area, you're going to start getting EE, and KE starts decreasing. You're going to start losing that kinetic energy because that chord is going to start slowing him down more and more and more. So now the bars are going to shift a little bit different. The gravitational energy is still going down. The elastic energy starts to go up, and kinetic energy now finally starts to go down. So still though, the total of all 3 of these in this whole area, at any particular point, if you could know what all 3 of them were, they would add up to the original total mechanical energy. Keep that, I can't stress that enough. The total is always, always, always the same as long as mechanical energy is conserved. That's the whole shebang that we're talking about. So keep that buried somewhere in your brain, or write it down where you write down all your important stuff. Put it on your cheat sheet. Definitely do that. And then finally here, at the 60 mark, he stops. So the kinetic energy is gone. KE is gone. And elastic energy is maxed out. We have the most elastic energy we can get. Okay? Now, that is explaining the energy transfer, so we know where everything's going. So we have a very clear picture of where all the energy is doing. Okay? Yeah. Alright. So I'm going to go ahead and do number 5 here real quick, since I've still got some time in this video. So, total mechanical energy of the system. So, I put in the hint, remember to think of a time in the process when you have enough info to calculate all of the energy the person has. Let's go back up to our explanation here. At what point in this, and I just mentioned it a second ago, where do we know everything about the energy that we have? Right there. At the 200 meter mark, you know that all of the mechanical energy is in the form of gravitational energy. The other 2 forms are not there. It's not moving, there's no kinetic, the chord is not functioning, so there's no elastic. All of the mechanical energy is gravitational energy. So that total is really easy to figure out there. All we need to know is GE equals mgh. I didn't get the equal sign in there. There we go. Okay, and we know all of that information. The mass is right here. It's 170. G is always the same number. It's always 9.8. And H, well, remember, this is at the top. So that is a 200 meter mark. So we can just quit making numbers, stupid computer. I told you all this would be ugly trying to do this typing. So GE, actually, let me just be clear here. Total mechanical energy equals GE. And that equals 170 times 9.8 times 200. And that, I've done this a couple of times, so I already know, it's 333,200 joules. There we go. So now this number is the total mechanical energy forever in this whole process. So this GE and this KE here in that second span, those 2 numbers better add up to 330,200. And in number 6, the most next relevant part, this part where kinetic energy is the biggest, well, that answers the first part of the question. When is the person moving fastest? It's right before the chord starts stretching. And how fast are they going? Well, here's how we can know that. The GE and the KE here in this part that we know that we have, they must 100% add up to our total mechanical energy. That's what conservation is. I'm going to keep saying that over and over. It is conserved. That means the number stays the same. Okay, so it's going to be at the 100 meter mark. And then next part of that, dang it. So we know that 333,200, that total amount, has to equal GE plus KE, because that's what we knew that we had there at that middle spot. And notice I always write the equation. Remember, that is such a good habit. Just it saves you a lot of time. Or not a lot of time, but a lot of mistakes. It saves you mistakes. As long as you have everything clearly laid out, you're less likely to just accidentally throw a number in the wrong place or something like that. And that's especially important with your IMA equations, because it's so easy to just, if you don't write the equation down, to just write the numbers in the wrong order, because they're all division, and if you flip them upside down, you've messed up your whole problem. So just make sure that you write everything out explicitly. Get in the habit of that. Do your math correctly, right? So like I was saying, so this 3,333,200, 333,200 equals mgh plus a half mv squared. That is the wrong thing. There we go, superscript. All right, so 333,200. Let's plug in all the information that I know. So again, mass is 170. We knew that from before. G is 9.8 still. Now at this point, remember, we're at the 100 meter mark now. So that height in the gravitational energy, that's going to be 100 plus a half. M is 170 still. And then V squared we don't know. Why does it keep doing that? Do the thing that I want you to do. There we go. All right. 170 V squared. And then you can solve that. So first of all, let's multiply this out. Since my phone seems to want to bother me so much, I'm going to actually do that on the calculator on the phone. So 170 times 9.8 times 100, and quit buzzing. All right, 170 times 9.8 times 100. I'm about to run out of time in this video. I need to go faster. So this is, I'm going to do this a little bit quicker. 1,666,000. No, that goes on the other side. 333,200 equals. So this is this. So plus a half times 170. Well, that one's a little bit easier. That's going to be 85. Go back. V squared. Okay. So now this looks pretty easy. Again, for those of you that it just bothers you to see algebra without x's in it, just change out that v to be x. It doesn't change anything. It's still the same problem. So if you like x better, by all means do x, but v is what we got here. So as usual with our algebra, you always want to do the opposite of everything that's there in order to get the letter v, in this case, by itself. So we're going to do everything backwards. So far we have 166,600 plus. So I'm going to do the opposite of that. I'm going to subtract it to the other side. And like I said, God bless it, I don't want to try to do this typing, but I would like to actually show my work here. But I'm going to subtract those on the calculator. So that 166 on one side is going to go away, and we're going to have 333,200 minus 166,600. Oh, well, it's exactly half. Duh, I should have known that. That's the nice part about it being the halfway mark. I feel like I planned that last year when I wrote this. Well, anyway, so that equals that, which is 85 v squared. So that we need to divide by 85 because it's 85 multiplied. So this number divided by 85 is going to give us 331,240 equals v squared. And then finally, we need to do a square root to get rid of that squared. So the square root of this is something, I don't think that this thing will go sideways. Oh, yes it will. So that number square rooted is, no, clear, I'm running out of time. You can do the square root. I'm about to run out of time in the video. The square root of this number is going to be the answer to number 6. I will pick back up at number 7 as soon as the next video starts.